Okay, well, welcome everyone. So in this video, I want to walk through the project milestone number 2 and some of the essential topics that we need to cover to be successful with this part of the project. Okay. Now, I mentioned some of this previously last time we spoke, but I want to have it here in a kind of recorded fashion for you so that you're able to reference it and check back in to make sure that it kind of clarify things that might have been a little bit confusing and give you some information to be able to reference. Okay, so a couple of things I'm going to talk about today. One is in terms of concurrent state machines, and the other is in terms of synchronous state machines. Right. We also have a couple other aspects that I want to talk about related to interrupts as well. So we really have 3 topics: interrupts, concurrent state machines, synchronous state machines. And I want to talk about, kind of go back and forth between conceptually what we're doing, as well as look at some code examples too. Okay, so let's take this one step at a time. Now I want to kind of remind you here that over the next couple project milestones, what we're heading towards is this idea of building functionality here. We've got the little LCD screen, we jump, right? We got the little hero character, we're able to move that character left and right. We're also able to have the hero character, when we press down on the button, jump up and land. Okay. All right, so we've got a couple different hardware peripherals that we're using to do this, and we're not going to have this all done. We're not going to have this all done in one shot, right? We're not going to have this done all in this one part of the milestone, that functionality I just showed you there. But I think it's good to know what the end goal is, so that as we're working towards it, you're able to keep in mind where we're heading. Okay. Now let's take this one step at a time, and I'm going to start by, after you have the joystick hooked up, I want to talk about something called an interrupt. Okay. And what an interrupt's going to do is this is going to allow us to trigger an event to occur. Okay, an event to occur. And I want to show this both conceptually as well as from the code perspective. Okay, now we want some function to be called. Okay, and particularly we want this jump interrupt service routine. We want this function down here. We want this to execute, but not in the traditional sense that we're used to. Excuse me, we're used to having code called by somewhere in the code. There is somewhere in there that we're actually calling this function. Okay, we're going to do something a little bit differently with interrupts, or really something that is referred to as event driven. Right, there's an event that occurs, an event that causes something that says, hey, this event happened, let's now call this interrupt service routine to handle that event. Okay, now we can think of the event as being the following. Imagine we have that joystick button. When you're pressing down at the button, imagine we're looking at that waveform signal. Okay, and it's a digital input signal, right? So it's a digital signal, so it's either off or on. And imagine the button's pressed, and we imagine that goes to a high state. Okay, and then the button's released, it goes to a low state, and then maybe it's pressed again, goes to high state, and then released. All right, so maybe we get a signal that looks like this. Okay, now what we really want, right? Imagine we want some piece of code to get called when that button is pressed. Okay. And particularly what we're going to do is we're going to trigger this that code to run at the rising edge of that signal. Okay, at the rising edge of that signal. Okay, so we're going to build a little piece of logic that is basically the code's running along, it's doing its thing, and we're going to interrupt the flow of the code. We're going to say stop immediately, right, because an event occurred, then run this. Okay, and then the code proceeds running right where it left off. Okay, so it's a different way of thinking. The code's running, it's running, interrupted, does something else, and then comes back to where it left off. All right, that's what an interrupt service routine is. Now, how we're going to hook this up in our C code in the Energia environment, okay, we're going to hook this up. Let me show you an example here. Okay. And ignore a lot of this code for now. I don't want you to get bogged down in details. I want to point out just a couple key pieces that are relevant for our purposes here. Okay, In particular, I want you to focus on these 3 lines. Well, one's a comment, so it's really these 2 lines. Okay, we're setting the pin mode, okay, and we're going to use an internal pull-up resistor. Okay, we're going to use an internal pull-up resistor as part of it. This avoids us having to necessarily hook up an additional resistor in our circuit. Okay, I'll explain more about that momentarily. All right, but before we kind of get looking too deep into that, let's look at this. Here we're actually attaching an interrupt. Okay, we have the pin here, and in this case I'm using pin 3, 6. Okay, I'm setting that digital pin to interrupt, so it's digital. Okay, I'm saying, hey, when that interrupt occurs, when that's triggered, run this interrupt service routine. So this is the name of a function. And then I'm saying we want this function, we want that interrupt to be triggered at the rising edge. Okay, those are the 3 input parameters into this attach interrupt. Okay, now if I look for this interrupt service routine here, okay, if I look for that somewhere in my code, and I've got this interrupt service routine listed down here. Okay, the only thing that interrupt service routine does is it's going to set a variable to 1. Okay, now oftentimes what you really want is you want these interrupt service routines to execute, you want them to be as small as humanly possible, and then you want them to return, right? And the reason for that is interrupt service routines are interrupting the flow of the normal program, right? They're stopping your rest of your code from running. You're now executing that, and then it's going to return to the normal flow. You don't want to tie up everything to have a whole lot of logic that might take an a period of time to run, right? You want them to be as small as you really can. So effectively, this variable here, you call it jump. I think in the project milestone, I called it jump flag, and you want them to be right where we're just setting it. We're saying, hey, the interrupt occurred, and then you're gonna have some logic somewhere else that then actually does something based on that information. Okay, all right. So that's how to attach an interrupt. Okay, and that will get it to work when the code, when we have a situation where we have that nice rising edge of the signal. Okay, you can imagine you can set the interrupts to work in different ways and be called in different types of scenarios. Okay, but it's a very powerful thing to deal with, right? So that's, when you're going through this part of the project, right, this is giving you a general sense of what's happening and why. Okay, now let's take a look at what we mean by here when we're saying the input level is an input pull up, right, indicating that we're using a pull up resistor. Okay, so we could look here at an example of an internal or a pull up resistor. And a pull-up resistor, as you've seen before, right, is we've got a resistor here that's connecting to our voltage source. Okay, and if we have our button over here then connected to ground, if the button is closed, right, we're going to enable current to go ahead and flow through our resistor down to ground. Okay, so basically if the button is open or the switch is open, we're going to have a high signal coming here to the input pin. And if the button is closed, we're going to have a low signal going to our input pin here. So depending on how the button's designed, whether it's pressed as closed or open, it depends on the characteristics, right? They're designed different ways. But we can have, because these are so common to have connecting buttons and other sorts of devices using pull-up, button switches, things like that, using pull-up resistors. Oftentimes our microcontrollers have them as that they're internal, right? That we have some sort of internal pull-up resistor that we can use. Okay, so this allows us to simplify our circuit a bit by being able to leverage an internal pull-up resistor for a significant amount of our logic. Okay, so we have the ability to do that. We can use this we could trigger using that pull-up resistor if we want to, using the pin mode here, input pull-up. Okay, that will enable it. Okay, if we do that, right, we can go ahead and leverage that as our way of connecting our our joystick, which is a pretty simple circuit to hook up, right? We can basically hook up all the wires. There's nothing too fancy going on there. We can use the resistor that is provided internally with inside the microcontroller. Okay, keep in mind, right? It's very important that we have a resistor between the voltage source and ground, because if we didn't, we'd have a short when the button's closed, right? And we have a connection. We better have a resistor here. Okay, and they're usually something around 10 kilo ohms or so for the resistor, for pull-up resistors in the case of buttons and so forth. Okay, so we talked about interrupts and gave some example of doing that. And now when you do the project, you're going to go ahead, you're going to test it, you're going to use the serial monitor to go ahead and trigger that. And one more thing related to the serial monitor here, or toward this logic, is I want to show you back when we pull up the code here. Right, remember, we're going to set this jump to 1, okay? And somewhere else in the code, we're going to actually use that information. Okay, so somewhere else in the code, we're going to actually look and say, oh, okay, did that happen? And then we're going to handle some logic accordingly. So let's take it one step at a time. All right, let's look at the next piece of information I wanted to introduce. And let's look at this state machine here. Okay, this state machine is what we're going to be using to handle the embedded control logic for our game. Okay, so this is going to handle all the actions associated with moving the hero character around. Okay, so what we have is this is an example of something called a synchronous state machine, and it's synchronized, and you notice there's something written here referring to a period. Okay, every quarter second. Every quarter second, right, we're basically doing a clock tick, right? And the way to think of that is we will not be able to change states. Okay, we do not move from one state to another or stay on the same state, okay, except every quarter second. Okay, the only time we can move from one state to another, right, is every quarter second. So that's both for state transitions as well as state actions. Okay, state transitions and state actions. We're having everything timed very nicely at these quarter second intervals. Okay, now you've heard me say this before, but I'll say it again. Why did I pick a quarter second? Well, the main reason is when we actually, it works out well, in particular when we have some of the, when we actually are refreshing the LCD screen, that clock period tends to work very well. If you do it too slow, the game's kind of sluggish. It feels very cumbersome and slow, and it's not very responsive to what you're doing. And if you make it too fast, the game gets a little blurry because the LCD screen can't refresh at that, if you turn something on to display something and then turn it off quickly, there's a little bit of a delay there. So quarter second tends to look well for visualization purposes on the LCD screen. Okay, we're not worried about the LCD screen just yet. Let's take a look at the state machine and let's get a sense of what's going on. Right? The big thing that it's handling is it's keeping track of where our hero, that little drawing of the little character, should be displayed on the screen. Okay, and X0, Y1, that is the bottom left-hand corner. Okay, so at the beginning of the game, when the game starts, it's going to just it's going to have the person in that bottom left-hand corner, and then at the next quarter second, it's going to be in this wait for action state. Okay, now if the person moves the joystick to the right, it's going to trigger something called the forward flag, and it's going to cause this transition to occur where we go to the move forward state. We're going to just bump the X location up by 1, and then we're going to immediately, the next clock tick, the next quarter second, fall back into the waiting for action state. Okay, very similar if you move the joystick significantly to the left. It's going to go here, move it back, and then fall back to the waiting for action state. Okay, the interrupt that we looked at with jump, it's going to trigger the jump flag, and the code example I showed was just called jump, but it's the same thing. Right, and we're using a melee type state machine, so we've got this action that takes place on the transition here. We're going to set count to 0, and we're going to stay here briefly. We're going to tick a couple times at this state with the Y being set to 0 so that we're now at the top of the screen. So we move the character up 1, right? And we're just gonna keep when the character jumps, it goes up and then hangs there briefly and then falls. Okay? Once we've ticked enough times, when it's basically when count equals 2, we're gonna fall back down. The hero location goes to 1, right? And we're gonna be waiting for action again. Okay? So this is handling, right? Each of these states is taking care of a particular piece of hardware, right? The player actions state machine is really taking care of the joystick operations. Okay, it's taking care of the joystick and the operations related to that. Okay, I'm going to go show you a little bit of an example here. Okay, and in particular, I've got, if I kind of look through this code somewhere, right, somewhere in here, I actually am reading the sensors. Okay, and I'm actually setting, this is equivalent to, the names are a little different than your diagram, but this is basically the forward flag and the back flag, right? Is the joystick to the right or the left, right? And if so, right, set the flags accordingly, all right? And what we have is a situation where we're doing the following. If you recall, we've kind of seen something like this before, right? We've got our loop, our infinite loop that just runs over and over and over again. And if you recall, right, I've got these different tabs here, right? One tab is the arcade project doesn't include much, right? I'll get to that in a second. If we were using the coin acceptor, which we're not, right, we have another tab. We have another tab for the joystick and another for the LCD, right? So I could name these different. I could have named this like the joystick one and the LCD one and so forth, right? They're each really, the coin acceptor, joystick, and LCD, they're all controlling some sort of piece of hardware, okay? Everything related to that piece of hardware, we're kind of separating the logic into, into a different tab, okay? Now, I want you to keep in mind something. Each one of these tabs is effectively called a thread. It's a different thread. Well, what is a thread? Okay, a thread is effectively concurrent code that's running concurrently. It's running effectively in parallel. And let me show you an example of that. Okay. So we could have, for our threads, we could have things like this. Right, where we have time moving down, right? And the threads, we could have one that's like for our joystick, right? One that's for our LCD screen, right? And we could have one that's kind of like the arcade project itself. We could have all these different things that are running concurrently, right? Now, in reality, what actually happens in reality is one will run for a brief period of time, the other will run for a brief period of time, then the other, and they switch so fast between them that they appear like they're running in parallel, right? So that if we can only run one thread at a time based on our underlying hardware, right? We have this where we can have this constant switching, right? Where we switch back and forth between each thread so quickly, but it appears as if logically they're running in parallel. Well, they might not actually be. Right? Now, one key thing about threads is what makes them different than having a full-fledged separate process running is that the threads can all share a common address space. Okay? And what I mean by that is the threads that are all running, okay, they might have some information, some local information that pertains to that thread, like some local variables, okay, that pertain to that thread, okay, but they can all be referencing some sort of global address space or basically variables, right? Things that are shared, data that's shared amongst them, okay? So that they're very, very handy and they could simplify things dramatically because what do threads allow you to do, right? Threads allow you to do something like this, right? Here's my arcade project, okay? I can have some stuff here that is shared across all of the threads. So some data here that's global across all of these other tabs. Okay, so for instance, the hero position, for example, right, is this XY struct. I can have this position here where the hero is on the screen, right? I can share that information amongst multiple threads. So it allows them to communicate amongst each other very easily. Okay. That's what we're doing by these different tabs. They're super, super easy to create, right? If I create one, I literally go here, I go to new tab, okay? That's effectively creating another thread. Very, very simple. Okay, couple things to note. The name, very particular, the name of the setup function must be the word setup followed by the name of that tab. Okay, I believe the first letter is always capital after setup, even if it's lowercase up here. I'm pretty sure that's the case. Okay, remember the setup runs one time when everything first boots up. Okay, loop, same idea. Loop followed by the name of the thread, and please make sure that the first letter of the name of the thread is capitalized, even if it's lowercase up here. All right, very particular to follow those naming conventions. Okay, or won't work properly, and sometimes you get very nasty errors with that kind of thing. Okay, it's as simple as that as creating concurrent threads. Okay, concurrent threads, and what we effectively have is state machines are really, really useful for controlling embedded control logic. We've seen that before, right? If you watch one of the older videos, we already kind of discussed why, right? And how it really helps with the logic dramatically. So I'm not going to rehash all that here, okay? But what I do want to talk about is something called a synchronous thread, and that we really haven't, besides some things that I showed you at the beginning of the last lab period, right? We're going to use this, what's considered a pretty ugly library. I think so. I think it has one of the really worst names of any library I've ever used. But if we look at this one here, and I'm actually sharing this library across all of the threads, I have this 1ems task timer.h. Okay, what this allows me to do is to create a timer that's going to cause all of our actions to occur at nice, clean, steady intervals. Okay, so what I mean by that, right, is let's take a look at it. Here, I'm creating something called a time that I'm naming timer task. Okay, I'm setting it that every 250 milliseconds, I want to call this player action timer interrupt service routine. Okay, so unlike the other interrupt that I showed you earlier, the other interrupt that triggered on a rising edge, this one does not. Okay, this one triggers every quarter second, so it's going to trigger at very steady clock ticks every quarter second. Okay. What is going to happen is this is going to cause this interrupt service routine to run, which is going to set this timer flag to 1. Okay, it's going to set that timer flag to 1. Okay. What that will do in our code is, let's take a look at our loop. You could ignore this play game. That's basically handling if the game's over. We'll talk about that later. We have this loop here that all that's going to do is if our timer flag is 0, it just keeps waiting 10 milliseconds. Right? It's good to put a delay there so that we don't eat up our processing power. This is something, if we don't do that, it's particularly called something called busy waiting, in which we're tying up our CPU, right, or we're tying up our processor, just constantly in this tight loop. A little delay makes it that we're not tying up resources as much, which tends to avoid problems. Okay. What this is going to do is, right, it's just going to continue to wait, doing nothing, until that interrupt occurs every quarter second. When that interrupt occurs, timer flag set to 1, so it leaves this loop. We then go here, set it back to 0, say, okay, we've handled that interrupt. We're doing something with it. I read the buttons. We saw this earlier. This actually sets the forward flag to 1 or the backwards flag to 1. Okay? And then we're calling something called the tick function. The tick function. Okay? And what does the tick function do? Well, the tick function is broken up into two pieces. Okay, two pieces. And please reference Zybooks, right, and some of the examples in past video as well to make sure this is really clear. Okay. The first switch statement is all of our transitions. All of our transitions for the state machine. Okay. This is your transitions like located here. Anytime we're going from one state to another, right? It's the logic that determines, hey, should we be going to a different state or staying where we're right where we are, right? So the first switch statement is all of the transitions between states, okay? And I'm not going to go through all of this for you, but like we could see the stuff like, oh, if we start at the initial state, the next thing we're going to go to is the game start state, right? There's no, we're always going to do that. There's really no reason, there's no time we would not do that. At the next clock tick, we're always going to go to that next state. Okay, same with gate start, we're always going to go to the wait for action state, right? We can see that here, there's no conditions that stop us from ending up here in the wait for action state. Okay. Now in the wait for action state, it gets a little bit more complicated, right? If we had that interrupt trigger a jump, we're going to go to the jump state. Okay, if we had it trigger, say, hey, we're going forward, we're going to go to the forward state. And if it said we're going backwards, we're going to go to the back state. Okay, so it's determining when we want to transition between these different states. Okay, that's everything going on there. And I'm not going to run through all of it, but just kind of give you the basic idea. Okay, what are the rules that occur for transitioning from one state to another? And then the player action state, the next switch statement is saying, okay, if now based on what state we're in, what should we do? Okay, and this is things like, you know, having initializing the hero location. Wait for action basically does nothing. You could ignore my comments in here. This is creating kind of some of the solutions and organizing things a bit better. We've got like things like, you know, the move forward. That's all. It's just like what the state machine's showing. It just moves it forward one, move backwards, and so forth. Okay, so so effectively, this, or just to recap, right? This tick function is going to do two things, right? It has one switch statement that handles all of the state transitions, and then the second one handles all of the state actions. What actually happens at that state, okay? All right, now, I intentionally, oftentimes when I create videos, I try not to be too repetitive because I know you've got the power to stop, watch it over again, go back, and do it as many times as you want. So I'd rather be quick and efficient whenever possible and give you the power to go back when appropriate to rewatch things that you're confused about. Okay, this is not a substitute, these videos, for going through Zybooks thoroughly, right? There's a lot of really good information there. And it's also not a substitute for really troubleshooting and working through a lot of these problems, okay? I guarantee you, as you work on this project, you're not going to have it be where you try something for the first time and it works no problem. Okay, maybe it does for a couple parts of it, right? But chances are you're going to be, as you work through it, you're going to hit a roadblock, and you got to troubleshoot and you got to isolate what's causing the problem, right? The serial monitor is your friend. Okay, make sure you have that set up, right? Print things out to the serial monitor. It's going to be very, very helpful for you to trace and debug problems. All right, and stay on top of it. Don't let the project pile up on you. Okay, so stay safe, everyone. All right, I'll see you at the next class or lab.